Okay, so new section. Let's talk about level sets. So level sets are kind of an alternative way to draw a picture to help you understand a function. And remember, my big thing about graphs is that they are an alternative. They are a geometric option, right? They're a way that you can draw a picture to help you understand functions. Level sets are a different one. And in certain circumstances, much better than graphs. Okay, so let's go through the details here. So here's the definition of a level set. A level set of a function is a set of this form. So now let's walk through the details of what this says. This says we're looking at all points in Rn, namely the domain, such that the value of the function at that point is equal to a designated specific value. Let's call it C. All right. So I'm going to designate an output value in the target, right? And the level set is the corresponding points in the domain, that the function sends to that designated output value. Okay. Now, well, I'm going to draw a bunch of pictures. But before I do, I want to point out, y'all have actually seen a bunch of examples of these kinds of things. Anyone who's ever watched the weather on the news has seen pictures of level sets. So let me draw that picture. Do I already have that drawn? No, I guess I don't. So I'm going to make a bad attempt of drawing the United States here. Let's see here. So something close enough, right? And what we've all seen pictures of is this thing where, okay, well, it's really hot. I need to be in pen mode. Okay, so it's really hot down here in Texas. I'm from Houston. I can tell you this is true. So there it's when it's really hot in Arizona, right? And then it's maybe not quite as hot, but still hot in this strip here. Something like that. And then, warm, but not that bad. Over here, let's say, and then it's just downright pleasant. In this range, and then maybe cold everywhere else. Something like this. Okay. All right, now the way that they will describe this is they'll write on here, they'll say, 90s, and they'll say 80s, and 70s, 60s, 50s. Okay, so everybody's seen these kind of pictures, right? Okay, so I claim that what implicitly they are drawing here is a picture of a bunch of level sets. Specifically, let's talk about what is the temperature on this curve. Right here, this is the curve that's on the boundary, if you will, on the boundary between the 80s and the 90s. What value is on the boundaries between the boundary between the 80s and the 90s? Well, 90. So this is t of x comma y equals 90. This curve is the set of points in the domain of our temperature function for which the output value is this pre-designated value 90. And then analogously for these others, so this curve right here, this is a level set. This is a different level set. This is where t is equal to 80. And then on down the line, maybe I won't do the rest of them because it takes a minute. So sure, they draw the colors to represent sort of the ranges, but really what they're doing is they're drawing curves. Right? And the curves are level sets of the temperature function. Okay. So there's other kinds of these kinds of things that you may have seen. So by the way, those curves are called isotherms. Iso meaning same and therm meaning temperature. Right? So points that all have the same temperature. So again, the picture we were just looking at. But you can talk about isobars. Isobars are analogous curves of points that have the same barometric pressure. So that'd be, if anyone was interested in the barometric pressure, they would draw those kinds of pictures on the news. Whatever quantity you might be interested in, a generic term is isoquants. They talk, if you're interested in some function, some value that's relevant in economics, that's depends on different values in different places. Maybe the price of gas as a function across the United States. You could draw isoquants. Right, those would be curves where gas is all at the same price everywhere on that curve. And that would help you understand how, in the same way that this picture helps you understand how temperature is varying across the United States. Right? An analogous picture with the price of gas would help you understand how the price of gas varies across the United States. It's kind of a picture. Here's another one, contour lines, and I guess I didn't list that in here, but contour lines, if anyone's ever gone hiking, you may have seen pictures of the way they draw the map. And let's say there's a mountain that you're interested in climbing. You might see pictures that look kind of like this, right? This is helping you understand the topography of the mountain. What is this? What is height depending on where you are in the vicinity of this mountain? And what you see is, so this curve here, this is maybe where altitude is 1,000. This is where altitude is 1,200. And then this is where altitude is 1,400, 1,600, and maybe that point there, 1,800. And this tells you a lot about what the mountain is shaped like. For one thing, it tells you it's a lot steeper in this little part of the hike, right, than it is in this part of the hike. Both of these red arrows raise you up 200 feet. Right? Here you're gaining 200 feet over a very short distance. It's super steep. Here you're gaining having a leisurely pace over a great distance to gain that same 200 feet. Okay. All right. So there's lots of real-world examples of these kinds of things. Very useful. Now let's take an algebraic example. Let's look here at, here's a function f of x1, x2 is x1 plus x2. Let me remind you, we just drew the graph of this thing. The graph of this thing was a plane in space. Let's go back to it here. Yeah, there's the graph of that function, plane in space. And by the way, hard to draw. It's kind of a pain to draw this. It's kind of coming out at us. It's a challenging artistic impediment. Okay, so let's draw some level sets of this. Level sets are what you get when, let's look back at the definition. Level sets are what you get when you set the function equal to a constant. No new variable. We're not inventing a new variable to represent the value of the function. We're just setting the function equal to a constant and looking at the resulting equations in the domain. Okay, so here, let's set x1 plus x2 equal to, various constants. If you set it equal to 0, you get that curve. If you set it equal to 1, you get that curve. If you set it equal to whatever other constant, c, maybe let's say 3, right? Then you get that curve. And this is just, again, a different way of helping you understand what this function is doing. This is telling you that the function has all the same values as you move in these directions. Okay? Which, again, you can kind of see that from the graph. Going back to the graph here. Right? The function's got the same values as you move in those directions. Right? And furthermore, you can see the function is increasing in value. Colors. The function is increasing in value as you move that way on the plane. Well, you can see that here. The function's increasing in value as you move that way. So now, which picture is better? It's pros and cons, which is helping us understand the function better. This picture's got a lot going for it. It's easy to draw. It's a picture in 2 dimensions. I have 2-dimensional paper. What I'm drawing on this 2-dimensional paper are curves, 1-dimensional curves. I have a 1-dimensional pencil. Again, match made in heaven. Man, it is perfect. This is so easy to draw. Whereas this graph picture, challenging. I'm trying to draw a 2-dimensional surface, right, with a 1-dimensional pencil. I'm trying to draw a 3-dimensional setting on 2-dimensional paper. It's very fraught, right? Not to mention the challenges of this particular plane that's kind of coming out sort of toward us, and it's just weird to draw specifically. Okay, here's a common complaint students make. Students think back to, the good old days of Calc 1 and Calc 2 and drawing graphs, and make the following observation. This graph here shows every point, right? Every possible value that could go into this function. I have a spot on the graph that's telling me exactly what is the value of the function at this input point. You might say the graph is complete, right? Whereas level sets, they have these gaps in them. Let's look at this level set here. I mean, I've drawn a bunch of level sets. I say a representative collection of level sets, but there is no indication sort of in between here. Hey, where is f equal to 2.5? It's not there. Great big gap, a hole. So the level sets are an incomplete way of representing a function. Yes, right? I confess that's true. But now let's take that criticism and go back and look at this graph here. The plane that is this graph is complete, but I didn't draw the whole plane. Because again, I got a 1-dimensional pencil. I'm trying to draw a 2-dimensional surface, right? I didn't draw the whole plane. There's a whole bunch of blank paper right here. Right? I didn't draw anything there. I have to figure out how to draw various other things to psychologically convince you that you're seeing something there, but you aren't. There's nothing there. That's blank paper. And so there are gaps in if you're using a pencil to draw graphs of functions of 2 variables, some pretty darn good gaps in that as well. I don't think it's at all clear that graphs are better. In fact, in this kind of a circumstance, very often I think level sets are just an easier way to get geometric intuition about what your function looks like. Right? I mean, imagine, what would be the alternative on the evening news, looking at the weather? They draw a graph of the temperature function. Were they going to walk out there with a 3-dimensional model? Say, hey, but here's the United States, and look at higher means hotter, right? And then they'd be like, okay, so here's this 3-dimensional model, and look how high it is over here. That you can't tell from your angle, but these points are sitting right above, Arizona. Here, let me try to tilt it so you can see that. Right? But it's a ridiculous proposition to have a graph representing the temperature function. This works great. Imperfect. Great. Yes?
Doesn't it still run into the same limitations of not being able to graph them, for example? Or
Oh yeah. No. Yeah, you're quite right. I mean, if I have a function of 17 input variables, you're quite right. The level sets fail as well, right? But in this circumstance, level sets are doing great, and graphs are already kind of on the ropes, kind of not really working so well. But you're quite right. I'm not saying that this resolves dimension problems completely, and it certainly does not. Likewise, contour lines. Nobody's going to carry around a 3-dimensional model of the mountain that they're climbing as they're climbing the mountain. That's ridiculous, right? It's very convenient to have it flat. And again, arguably, you can kind of see more information. There are things that you can see with level sets that you just cannot see on a graph. I can see exact points where the altitude is a certain convenient value like 1,000. On a graph, if you have a surface, you'd be like, well, these points here, but I don't know where they are. You'd be trying to visualize what points on the map, what longitudes and latitudes correspond to the altitudes you're looking at. That wouldn't be visible on a graph. On a level set, it's great. Okay, so that's what level sets are. A quick thing about notation. I want to talk about this notation that I used in that picture. We can call this a preimage notation. Let me draw a domain here and a target here. And if you have your function like that, all right, then given a point here, the output value, this is called the image of that point. Right? We've talked about the word image before. We talked about the image of the function. Here I'm just talking about the image of just the one point. Okay. Well, if this were an invertible function, then we would say, okay, then this is f inverse and then this would be, I guess you might call this point here the image of the inverse function. But another pretty convenient little bit of terminology would be to call it the preimage of that point. So image says what comes out of f. Preimage says what comes out of f inverse, if you will. Okay, so in this context, the function is not invertible. You can't talk about the inverse of a function like this because, it's just not invertible. I mean, it's easy to see that it's not invertible. There are plenty of points here that all have the same output value. Which one of these is the inverse of 90, right? T inverse of 90. Well, that's not a single point. So even though it's not invertible, even though the inverse, T inverse it's not a function, nevertheless, all of these things go to 90. It's tempting to say, if you were to turn it around, 90 has as its preimage all of these points. So it's a convenient little terminology and notation. We say preimage. You'll notice this notation as if f were invertible, which it probably isn't. But this is not to be understood as an inverse function. This is just intended to be suggestive notation describing that we're looking at the preimage. We're looking at the set of all points whose outputs are C. Okay. Alrighty. Okay, so let's talk about the relationship between level sets and graphs. Now they are different. There we go. Okay. Yeah, well, I want to fit both of these on this page at the same time, and there's not much writing here, so I think this is okay. So let's suppose we have a function of two variables, x and y, and recall that if you want to make the graph of a function of two variables, x and y, you know what, let me go ahead and zoom back in. We'll zoom back out in a moment. If you want to make a graph of a function of two variables, x and y, you set the value of the function equal to a new variable, z. You write that equation, recognize that this is now an equation of three variables, and you draw the resulting surface, and I've drawn an example surface here, some sort of wacky, bended bowl kind of a thing. No particular reason, I just wanted to have a picture to be able to draw. Okay, so what do you suppose would happen if you take, as you see as I'm doing here, a horizontal cross section of such a surface? Well, you're going to get some curve. Okay, so we've got a function, we're looking at the graph, we're taking a horizontal cross section, you might say a level cross section of that graph. We get a curve. But now, let's think about what's happened here algebraically. We've set f equal to z, then we've set z equal to c, right? All together, we have set F equal to C. Right? This cross section is where F is equal to C. That cross section is a level set of the function. So this is a nice punchline. Graphs and level sets, different constructions though they are, importantly different, dimensionally different, have a nice close connection to each other in the sense that cross sections of graphs make level sets. And now let me zoom back out. The way you would represent this as a level set, you wouldn't draw that whole three-dimensional picture, of course. Level sets live just strictly inside of the domain. So it's a little bit of a sloppiness for me to say that the cross section of the graph is exactly the level set. I mean, technically, the cross section of the graph is a curve sitting up in space at height at z equals c, which if I were to ignore that z component, that curve is exactly the level set in the xy plane. And okay, well, yeah, sure, but it's very comfortable, I think, to ignore that z and say, when you take the cross section, let's just think about the resulting equation in terms of how it relates x's and y's, and with that understood, the cross section is the level set. All right, how are we doing on that? Is everybody okay? Okay. All right. Let's see, I think I have an example prepared for that. Yeah, here we go. So let's look at this function here. We've studied this function before. Let's make the graph. The graph of that function. Remember the rule for graph? If you want to graph a function, you create a new variable, you set the output value of the function equal to that new variable, in this case z. That gives you an equation, and then you draw the solutions to that equation. This is our old friend. This is our paraboloid surface. And we know what that looks like. That looks like, whoops, where did I draw it? Yeah, here it is. That's this. Okay. And the observation that we've made moments ago is that if you take a cross section of that graph, right? So there I am slicing z equals c. That cross section should be a level set. Well, the cross sections of this bowl are clearly, why don't I start calling it paraboloid? It's called a paraboloid. The cross sections of this paraboloid are circles, right? And of course, the level sets, what you get when you set the function equal to a constant, are also circles. Right? So here's the graph, here's the process of taking cross sections to get level sets, and the resulting picture of, how would I understand this function from a level sets point of view is I would draw a bunch of concentric circles representing the values of the function as z gets higher and higher, as the value of the function gets higher and higher, you're at further out rings on this picture. So, again, you have to decide, which one of these pictures do you like better? I will admit that there is a certain appeal to this picture, this graph picture, because, well, this is a pretty simple surface. It's got a lot of symmetries. My imagination will allow me very satisfactorily to kind of see that which has not been drawn, right? And so the graph picture here is kind of nice. It's fine in this sense. Like here. Whereas, the level set picture, it has the disadvantage that, it is, it's got gaps in it and stuff like that. But nevertheless, there's a lot of information in this picture. In terms of communicating details, I think it's a kind of a wash in this case. Okay, so let's talk about pros versus cons on this. One of the big advantages, I've already talked about this, but the dimensional advantage of level sets is enormous, right? You have a function of two variables. The graph is a challenging art problem. How do you draw a surface in space with a pencil and two-dimensional paper? That's hard. Right? Whereas level sets, no big deal. Further in that same direction, let's look at this function. F of x, y, z is x squared plus y squared plus z squared. This is a function of three variables. How would I draw the graph? This is a four-dimensional picture. I can't even fake it. It's out of the question. The graph is a useless concept for this function. For us, mere three-dimensional mathematicians. Okay. But the level sets, well, the level sets are what you get when you set this function equal to various constants. And if you write that, notice we have various equations of three variables, which, yes, they are a little annoying to draw, but in this case, they're all spheres. Right? We have a bunch of concentric spheres, and I can draw a bunch of concentric spheres. And I'll whine about it a little bit because it's hard, and it's how do I make it look three-dimensional, and there's certain challenges to that. But I can kind of do it, as opposed to graphs, out of the question, off the table, not possible. Okay, so the dimensional advantage is a big deal. Here's another really nice. Oh yeah, sorry. Go ahead.
In the discussion, it says ranking R3 to R1.
Yeah.
R3.
Yeah, right. That's right. So that's the nice thing about level sets. Now graphs require one dimension for each of the variables, right? Each input and each output. Level sets don't. Level sets take place in the domain. Yeah, because let's look at this as an example, right? This has three input variables, x, y, and z. Level sets are what you get when you set the function equal to a constant. That gives you an equation involving x, y, and z. There's no new variables. The output values are not involved other than as part of the equation that we write down in the domain. So yeah, that is the dimensional advantage. Absolutely. Yeah.
So for example, we could do R3 to R1 with a 3D graph, but couldn't really do R2 to R2.
So we can draw level sets. So I think I heard you say graph, and I'm not sure you meant graph.
I didn't mean graph.
Okay, yeah. So we can draw level sets of a function from R3 to R1. That's surfaces, right? Level sets are a little bit weird if you're going from R2 to R2 because they tend to just be points, and it's kind of level sets are mostly useful when you're looking at single output variables functions. So yeah, all we're going to talk about in this class, in fact, are what we call real valued. So single real valued functions and their level sets. Yeah. Right. Okay. Here's another advantage of level sets. Here's a true fact. I've already actually made reference to this fact elsewhere. But if you're looking at any equation at all, it's big talk, any equation at all, it can be expressed as a level set of some function. Now, before I show you how to do that, before I show you again how to do that, I also already kind of, anyway, before I go back into how that works, let's talk about how nice this is. What a powerful result. Any equation ever? Really? My God, there's a lot of equations out there. Why would I care that I can write it as a level set of a function? Well, because what we're going to find as we go further on through this course is we're going to do a bunch of calculus, right? And we're going to, among other things, study the calculus of level sets. So, reminder, pretty much all of single variable calculus is calculus of graphs, right? We're going to understand sort of, geometric features of a curve based on what we know about the derivative and second derivative and stuff like that of the single variable function, but it's drawn on the graph. So we already know a bunch of stuff about calculus of graphs. We're going to come to find out some very valuable information about the calculus of level sets. So what this observation here is going to do for us is say, no matter what equation you have, once you choose to view it as a level set, which you can always do, then the calculus of level sets will always be a tool that will help you understand the solutions to your equation. So that means the calculus of level sets is universally applicable to equations. So, hey, maybe we'd better understand the calculus of level sets. And that'll be later on. Now how is it that we can write any solution set to any equation as a level set of some function? And again, I made a reference to this a while ago, but let me just remind you, whatever equation you have, right, you can just take this and subtract it over the other side. Now you've got a bunch of stuff, some function equals 0. And notice that this is a level set, right? We have set whatever function that is, we have set it equal to a constant, specifically the constant 0. So it's not that tricky of a move, but it's a very important and valuable move. Everybody on board? Okay. Calculus of level sets to come later. By the way, not true of graphs, right? So not every equation is a graph. Many equations are not graphs. We happen to have one here on the page, coincidentally, right? Let's look at this thing right here, this surface. This is described by an equation. That sphere is described by the equation x squared plus y squared plus z squared equals whatever. It's not a graph. Fails the vertical line test. Badly. So what you may understand about the calculus of graphs, not directly going to help you understand this surface. And again, I did not have to go into extreme, anomalous, weirdo cases to find an example of this shortcoming of graphs. Here's a really easy surface. It's not a graph. Okay. Okie dokie. So here's this is really kind of a corollary of the previous, but any function whose graph you're interested in, for whatever reason, can be viewed as a level set of some other function. So this is, again, a rip off of the previous statement. The proof of this is a very straightforward note that graphs are defined by equations, right? Y equals f of x. Or, y equals f of x1 comma x2. Or the point is, the construction of a graph requires writing down an equation. And all equations can be viewed as level sets of some function by just whipping everything over to the other side. Okay. So the reason I wanted to show this specifically here is that it sort of more directly rubs graphs' nose in it, right? That, graphs, we can always rewrite you as level sets, but not the other way around. Not every level set can be rewritten as a graph. Graphs are delicate. Just doesn't always work. Okay. The details of this, now again, you'll notice all I did here is whip this over to the other side in that algebra right there. Right? But let's just, to be thorough, let's observe here that we have a graph. That's the graph of this function f. And I claim that this is a level set. Now, I'm viewing it as a level set right there. What is that a level set of? Well, it's a level set. You can see equals a constant there. It's a level set of this function that I'm calling g. And very importantly, notice that the function f, hang on a second here, the function f, whose graph I'm looking at, not the same function as the function g, whose level set I'm looking at. Right? We have two equivalent equations. this is a graph, this is a level set, but this is a graph of one function, this is a level set of different function. The formula's different, right? This is not just f, this is y minus f. Y is an input variable to this function down here. Y is not part of the discussion of this variable up here. It's what we eventually call the output value. Anyway, these are very different functions, and you've got to, don't be too sloppy in the interpretation of this. So a sloppy misinterpretation is very common. Students say, oh, well, if it's a graph, then it's a level set. So I'm just going to, if it's a graph of f, then it's a level set of, I don't know, f. Right? Well, this is not true at all. If it's a graph of f, then it's a level set of a different, very importantly different function. Okay. All right. Okay, a bunch of exercises. I'm going to move along to parametric curves and surfaces. Parameterizations is a different way to think about what we're going to talk about here. Ultimately, this is going to be a different way to use pictures to understand functions. But it's also, arguably more directly, going to be a way to use functions to understand pictures. So the parameterizing, the role that it serves, the purpose that it plays is you can think of it either way. But anyway, that's worth it. Okay, I'm going to start off talking about images. Don't forget we've already defined the image of a function. The image is the set of actual outputs from the function, not to be confused with the target. The target is just a large, perhaps unnecessarily large world that I just need to know. When I'm applying a function, I need to know that my output values land in a well-defined place. So, whatever place the outputs are going to land. The image is the actual collection of actual outputs that come out from the actual inputs in this function, right? So you can see here the image is the set of actual values f of x in the target. Okay. All right. So I'm going to try to persuade you that if you have a function from R1 to Rn, so one-dimensional domain, n-dimensional target, I'm going to try to persuade you that we would expect the image to be a curve in Rn. Now, this is not a proof, and it's also not always true, but this is what we call generically. So, usually weird little examples to the contrary. This is usually true. And by the way, we're going to assume these functions are continuous. Let's not worry about regularity. Okay, so let me draw some pictures. So we're again thinking about a function from R1 to Rn. Let's call it R3. Oh, let's call it R2, just to make the picture a little bit easier to draw. So here's our domain, and the function takes points from the domain and spits them out into the target over here. And I'm going to just start plotting some points. Okay, so here's an input value, and f, our function there, is going to spit that out and someplace. Right, input, output. Okay. All right, now let's look at a nearby point. Again, we're assuming these functions are continuous, and more broadly, let's assume that these functions are nice, generic, nothing weird, right? You got a point that's near that point, you would expect the output to be near somewhere near that output. So let me say maybe it's like that. Okay, and then let's look then at maybe this point. Further along in the domain, well, maybe that output would be maybe something like that. And then here's another point in the domain. It's going to have an output maybe that's, let's say, about like that. And then here's another sort of moving over a little bit in the domain. Maybe that has this other output. And proceeding along, just to get a little bit more on the page. I'll end it at red. So what I've got here is a bunch of points moving along in the domain, and sort of successively each input point in the domain that I'm looking at are kind of nearby, proceeding along. And then, well, these outputs have to be nearby. They don't have to keep moving in a straight line, right? We've got all of R2 to work with in the outputs, but they kind of have to continue to be nearby, and so you sort of expect them to maybe trace out some sort of a curve. Right. In fact, you can imagine that, try to imagine a continuous version of this as you proceed along there. You could imagine sort of proceeding along in the outputs, something like that maybe. Curve. So this is just an attempt to persuade to plausibility argument. And in a surprisingly large number of cases, this is true. The outputs from such a function do make a curve. The image is a curve. Okay. All right. Okay. So a little bit of terminology. Let me just, I'm going to clean up this picture a little bit. Got this function there, f. Let's look at the target. Oh, I'll color this color. We have the image, maybe some curve like that. The terminology here, this curve is the image of f. Again, we've already talked about it. Now what I want to do is let's turn this problem around backwards and let's ask, instead of, suppose I have a function, what do the output points look like? Let's suppose that I instead have a curve. Let's suppose I start off with a curve. And what I would like to know is it possible that that curve might be the image of some function? Can I find a function whose image is that curve? And if you can, then we give this function a name. We say that this function is a parameterization of the curve. So these words kind of go, if you will, kind of different directions. Given a function, the image is the curve. Given a curve, the parameterization is the function. Everybody see how that language works there? You got to be careful. I mean, sometimes people will say this backwards and talk about the image of the curve. That doesn't make any sense, right? Or let's parameterize f. Doesn't make any sense either. All right. Okay. All right. So you can see this is, among other things, this is yet another way to use geometry to understand a function, right? So we've talked about in different ways to use geometry to represent functions. A graph of a function, some contexts, really useful. It's got its limitations. Level sets of functions, some cases very useful. They've got their limitations. Now we see the image of a function. In some cases, the image of a function is a picture that helps us understand that function. And in some cases, this is really useful. And it has its limitations. Now, one of the limitations here, I'm going to start off with only talking about what we call parametric curves. This being a curve, this curve being an image of the input axis here, we're going to consider only domains being R1. Just one single input variable. Images being just curves. And we will talk about what happens if you have two input variables in a little while. We won't get to that today, but that will be coming up real soon. Okay. Right. Okay. So here's an example. Let's look at this function right here. Notice this is a function with one input variable. It's function from R1 to R2. The target you see is R2. That means that the image of this function will be a curve because it has a one-dimensional domain, we would expect. A curve in R2. Notice that the image is always a subset of the target. Okay. So we're looking for a curve in R2, and how are we going to identify what that image is? This is a by hook or by crook kind of situation, and you kind of have to play various different games. I'm going to show you various different bits of trickery that will allow you to, in some cases, again, when they work, identify what the corresponding curve is. And in this case, what we're going to do is we're going to look at the output values. That's our X, right? That's our Y. In fact, why don't I label these? That's X. That's Y. And we're just going to try to find an algebraic relationship between these two formulas. If I can find an algebraic relationship between these two formulas, then notice that means I will have an algebraic relationship between X and Y, and we're really good at drawing pictures of curves that are algebraic relationship between X and Y. Algebra 2, yeah.
So when you draw the image, will that look the same as what the graph would have looked like?
No, it doesn't. That's a great question, though. So we have one input variable, two output variables. The graph of this would be a three-dimensional picture, right? The graph would be like a bunch of points of the form t, x, y, and it would actually be a line in three-dimensional space. The graph, again, we've got to keep in mind, graph is a very specific construction, right? Graph does not mean the picture that seems most conveniently in your circumstance to give you a vibe of what the function is, right? So graph is this very specific construction. There's three variables here. So the graph would be a three-dimensional picture. The image always lives inside of just the target. The target here is just R2. There are only two output variables, X and Y. So so it's going to be pretty different.
Would there be any geometric relation between the image and the graph?
I mean, kind of in a way, but it's. I want to discourage thinking in those terms. I mean, it's a very natural question to ask, right? But I think it's ultimately not a good good road to go down. So I'm going to suggest let's just not pick on that. Let's not pull on that thread. We can talk about it some other time if you'd like. Yeah. So what I'd like to do is just encourage thinking of understanding a function by its image as just a completely disconnected, unrelated way of understanding functions. Yeah. Okay, so can we come up with some algebraic relationship between X and Y? I've got a formula for X, I've got a formula for Y. And what I advise on this is, play with it. Think strategically. Follow your instinct, right? So here's my instinct. I see there's a T in the formula for X. And then I see a 2T in the formula for Y. So in order to make a little progress, I am inclined to look at that formula for X and multiply it by 2. And then I notice that 2X is 2T plus 2, which is starting to sound a lot more like 2T minus 1. Right? And then a little bit more sort of, play with it, keep kind of moving things around until you score. Not hard to persuade yourself, Y is 2X minus 3. Right? 2X, 2T plus 2. Subtract the 3, 2T plus 2 minus 3, 2T minus 1. Oh, that's Y. Everybody see what I'm talking about? So let's not try to turn this into a precise algorithm. I think that's counterproductive. I think the better way to think of this is sometimes when you feel like you see daylight and you think this is going to work out, just play with things until you get a score. Okay. So this equation then This is an easy equation, y is equal to 2x minus 3. Here it is. That's this curve here. So that curve is the image of this function. Or said differently, this curve, this straight line, is parameterized by this function. Yeah? Okay. All right. Okay, well, here, let me, I'm not going to spend a lot of time on the sort of the second half of this argument is, I have to confess, technically really all we showed here, I showed that every point in the image satisfies this equation. So technically I've shown that the image is a subset of this line. It is not necessarily immediately the case that every point on this line has to definitely for sure be an output from this function, right? This is we did the algebra sort of in only one direction. So there is a remaining little bit to show that every point on the line actually does come out of this function. It's just details, and it's I don't think it's a good use of our time here, so let's just not worry about it. Okay, here's another one. Different function, still R1 to R2, but notice how different that function is. This function's a cubic. Yikes. A little scary. Algebraically, is this going to work out? But notice that it still remains that, well, there's a t cubed there, there's a t cubed, well, there's 2t cubed, but hey, if I multiply this x by 2, then this starts to look more like that, but then the constant's off, and you play with it, and what you find is that you're looking at the same line. That's unexpected, right? Aren't cubics supposed to be like that or something? Right? Well, graphs. Yeah. Right? But that's not what this is. We're looking at images. This is a different way to geometrically represent things. The image of this function is the exact same line that we were looking at a minute ago. Said differently, that exact same line is parameterized by this very different function than the one we were looking at. So that's you could argue this is a very serious shortcoming of trying to understand functions by their images. The images do not distinguish these two functions from each other. The previous one that we just looked at, this cubic that we're looking at here, the image can't tell the difference. So, that's too bad. Let me say that same thing sort of backward from the point of view of parameterizations. If you have a curve, you have lots of different ways that you can parameterize it. And you say it that way, and it's like, oh, well, that's arguably kind of a good thing. I have choices in how I parameterize. And maybe that's nice. Okay. You may have noticed, you know what? I'm out of time. Okay, no worries. We will stop right here for today and pick up here tomorrow. Reminder, tomorrow we do have a weird day because the Marine Lab people have to come in here, and I don't know exactly when they're going to need to start setting up. So we might have to cut class a little bit early tomorrow. We'll see when people start accumulating outside the door there. And then also email me if you're interested in going to Beaufort. Okay, see y'all later. Oh, and especially email me if you have a car.